All right, everybody, welcome to Math 470 Algebra 2. We are continuing to talk about algebras over fields. Today we are going to talk primarily about something called the exterior algebra, but in reality it's sort of an application of the tensor algebra which we saw last time. Okay, so just to recall, we constructed last time the tensor algebra over a vector space V. So we assume V usually is finite dimensional. It can be infinite dimensional, but we're going to stick to finite dimensional case. The zeroth tensor power is just the base field. The first tensor power is just V. The second tensor power is spanned by all tensors of V with itself. More generally, the nth tensor power is everything from the n minus first tensor power tensored with something from V. And then the tensor algebra itself is the sum of all of those spaces. The thing to remember about the tensor algebra is that it is what we refer to as a free algebra. So it has the most free associative product on it. When I take V and I tensor it with W, I get V tensor W. I just get what you get when you multiply those two things together. Now, the reason we want this is the tensor algebra gives us something referred to as universality. All right. The tensor algebra itself is not tremendously interesting because it's free. But what's interesting about it is that when you're given an associative algebra over a field K, you can usually find a vector space V such that A is isomorphic to the tensor algebra modulo some ideal. All right, we saw a very basic example of that last time, which is that if you take a single one-dimensional algebra over K, so it's got some basis X, and you take the tensor algebra, you get essentially the polynomial algebra. Well, not essentially, you do get the polynomial algebra. It's just got a bunch of tensor symbols written in it instead of X to the N. In this case, this ideal, there isn't one. Okay, we just simply take the trivial ideal. We mod out by 0, and so nothing happens. All right, so today we're going to look at a couple of examples where that ideal isn't 0, and you start to get some more interesting structure. Okay, so let's slowly increase the dimension. All right, so we've looked at what happens when you take a tensor algebra with a one-dimensional space. All right, so let's take a second example where we're going to take a two-dimensional space. So we're going to have two indeterminates, essentially x and y. They're going to be our basis vector. All right, now we're going to take an ideal I that contains everything of the form x tensor y minus y tensor x. It's going to contain x tensor y minus 1. And we don't have to include this, as we will see, but we're also going to throw in y tensor x minus 1. Now, why is it optional? If we assume that these two things are in there and we have the smallest ideal that contains those things, it turns out it will contain this one as well. All right, now we're going to take an algebra where we take the tensor algebra on V with these two basis vectors x and y, and we're going to mod out by this ideal, and we want to figure out what this thing looks like. Okay, so what is this thing? All right, so the idea is to start with your tensor algebra and determine what the ideal does to it when you take the quotient. Now, the thing to keep in mind, when you take the quotient, anything that is in the ideal becomes 0 in the quotient algebra. All right, so that means, in particular, those three things that I made certain were in there. X tensor y minus y tensor x, that's now 0. That's what's going to happen when I mod out by the ideal. All right, since this product is no longer free, we're going to drop the tensor notation. So what this means is in the algebra, in the quotient, xy minus yx is 0, or equivalently, x times y is equal to y times x. All right. Similarly, x tensor y minus 1, that's now going to be 0. So that means that x times y in the quotient is going to be equal to 1. And then similarly, yx is equal to 1. Now, as mentioned, this is optional. Why? Well, this here, xy is equal to yx. So that means, in particular, this algebra that we've constructed, this quotient, it's commutative. So knowing that x times y is equal to 1, I didn't need to throw this in. Y times x has to be equal to 1 because I know x times y is y times x. All right. Then this statement, though, well, that tells me that x times y is equal to 1 and vice versa. So in particular, that means we've made y into the inverse of x. So we can, therefore, replace y by a symbol we will call x inverse. All right, so everything in there is linear combinations of x and y, or more to the point, linear combinations of x and x inverse and their powers. All right, so we get what's called the algebra of Laurent polynomials. This is polynomials of the form of this form here, where the power runs from some finite negative power up through some finite positive power. And you have component-wise addition with distributive multiplication. If you've taken complex variables, you may remember Laurent series. This is where these things get their name. Laurent series are power series that have negative powers involved. Laurent polynomials are just polynomials of that form. They don't go on forever like a power series does. Now, the advantage to doing this is that we've constructed a nice algebra and we don't have to verify any of the algebra axioms. They all come for free because we know it's a quotient of a tensor algebra. And really, we can do this with almost any algebra. It's just a matter of trying to figure out what vector space to start with and then what ideals to use and what relations to put into the ideal. Okay, so that's a nice little example. But now we're going to look at something really important. So much like the tensor algebra, this can be done on any vector space. So again, we're going to assume finite dimensions. You don't actually have to. It can be infinite dimensional. All right, and it's going to have a basis v1 through vn. I'm going to take the tensor algebra, and then I'm going to take the smallest ideal that contains all of the following quantities. The first thing I wanted to do is I wanted to contain v tensor v for any v and v. I also wanted to contain v tensor w plus w tensor v for all v and w and v. Now, we're working with a vector space, so I could just throw in the basis vectors. So vi tensor vj with vj tensor vi, and that would be enough. Linearity and sort of closing out the ideal, multiplying on the left and the right, would get me all v and w. Okay, so we're going to throw all of those things into the ideal, and this leads to what is referred to as the exterior algebra. The exterior algebra is denoted with a wedge. That's this shape here. All right. It is this tensor algebra modulo the ideal, described above. The other thing, though, is that we can do what are called exterior powers just like we do tensor powers. I have the nth tensor power. The nth exterior power is just the image of the nth tensor under the quotient by the ideal I. So this means that much like the tensor algebra, the exterior algebra is a sum of the exterior powers. And instead of writing v tensor w plus I, I'm just going to represent that as v wedge w. I accidentally omitted these indices, so I've added them back in. Technically, this is going to run from 0 to infinity, much like the tensor algebra does, but we're going to see that in the exterior that this actually gets severely truncated and actually will become a finite dimensional algebra. Okay, so to get an idea on the exterior algebra, we're going to do the same thing as we did with the Laurent polynomial example. We're going to look at these relations that we've put into the ideal. Those things will all become 0 in the quotient. So what does that tell us about the algebra? All right, well, in particular, we said V tensor with V had to be in the ideal. So that means in the image, V wedge V is 0. So any vector multiplied by itself is 0. So every vector is nilpotent in particular. Okay, we insisted V tensor W plus W tensor V be in the ideal. So that means V wedge W plus W wedge V is now 0. So in particular, if I want to reverse the order, it won't commute, but it'll come close. If I reverse the order on the product, I pick up a negative. All right, now, it's not immediate, but this turns out to be true in general. If I've got any large wedge of vectors, if I have something in the ith position and something in the jth position, and I want to reverse them, I can. It's just going to cost me a negative every time. So when this happens in an algebra where a times b is negative b times a, it's almost commutative, and so we simply call it anti-commutative. Reversing the order just induces a negative on the product. In many cases, while commutative is kind of the nicest case, anti-commutative is close enough. Okay, now, tensors are multilinear. If you remember from that last screencast, if I hold all other variables constant and I've got a sum in the ith, I can treat it as linear in the ith position. So I can break up a sum, or if I've got a scalar, I can factor it out. Nothing in our ideal is going to change that, so wedge or exterior products are also multilinear. I can, as long as I hold everything else constant in the ith position, I can expand any sum and I can pull out any scalar. All right, so let's talk about basis and dimension. So we've seen the tensor algebra. We managed to basically build up a basis by taking the tensor of basis vectors with basis vectors. Well, what's going to happen here? Well, all of our relations in the ideal dealt with using at least 2 vectors. So in particular, the 0th tensor power, which is just always defined to be the base field, that's not going to change when I mod out by the ideal. The base field will remain there. And similarly, if I take the first tensor power, that's just the vector space. Well, again, all of my ideal relations involve at least 2 vectors being multiplied together. So it doesn't really kick in until the second tensor power. So the first exterior power of the vector space is, again, just the vector space. That doesn't change. Now, what happens when we get to the second power? All right, well, the second tensor power is spanned by the tensors of anything from V with itself. All right, so with V having basis V1 through Vn, we saw last time that the second tensor power has a basis of Vi, Vj, where Vi and Vj are any 2 vectors from the basis. And so in particular, the dimension of the second tensor power is n squared. Now, these form a basis of the second tensor power, so when I pass them through the quotient, they'll still span. That won't change. All right, so if I take the image of Vi tensor Vj, that's Vi wedge Vj, and it's going to be spanned by all of those, but now the relations start to kick in. All right, in particular, for the tensor power, Vi tensor Vj and Vj tensor Vi are linearly independent vectors. They are different. All right, but that's no longer true here. These vectors are not linearly independent. Reversing the order on the wedge just induces a negative. Okay, so this vector is a linear combination of this vector. It's just a multiple. So I can't have both of those in the basis. They wouldn't be linearly independent. All right, so those are going to be cut away. Moreover, VI tensor VI, that's just whatever you get when you tensor VI with itself. But now, in the exterior product, that's 0. So those can't be in the basis either. All right, so what is a basis going to consist of? Well, I am going to need VI and VJ where they are distinct, but I don't want repetitions. If I've got VI wedge VJ, I don't want VJ wedge VI as well. So to make certain that that's excluded, I will take all VI wedge VJ and I will just assume that the first index is less than the second index. Okay, those will turn out to be linearly independent. So how many do we have? Well, my basis would consist of taking the wedge of any two distinct basis vectors, and I put them in the order of the first index before the second index. But basically, I have to choose any two basis vectors from my basis. Well, there are n vectors in the basis. I need all pairs of them. So my dimension will be simply n choose 2. Okay, now note all of this was the effect of anti-commutativity, and there really wasn't anything special about looking at 2. More generally, if I look at the k-fold wedge, and there's a typo, hold on. Okay, so the tensor, k-fold tensor power is spanned by all k-fold tensors where I take each one of these from the bases. All right, well, that means the k-fold exterior is going to be spanned by all of those k-fold wedges. But again, the anti-commutativity is going to affect the linear independence. So if I have a k-fold wedge, if any two of those vectors are equal, then it's 0. So I can't have a repetition. All right, likewise, if these vectors, as I looked at their index from the basis, if they're not in increasing order, I can just move them around. I can flip two of them, any two that I want, and it turns out that's enough. I can reorder it in any permutation I want. It may cost me negatives, but in terms of a basis, that's okay. So my basis is going to consist of all k-fold wedges where I can assume that the index of the basis vectors is strictly increasing. Again, that means to make one of these, I have to choose k distinct vectors from my basis. The number of ways to do that is simply n choose k, so the dimension of the k-fold exterior power is simply n choose k. Okay, so as I mentioned earlier, the exterior algebra is going to get severely truncated compared to the tensor. The tensor is very infinite dimensional. The exterior isn't, all right, because in the k-fold power, I have to choose k distinct vectors. Okay, well, in particular, if k is larger than n, I cannot choose k distinct vectors from n vectors. So that means the largest exterior power is n, where I take all of the vectors from the basis into the wedge to make a basis vector. All right, so it has now only got finitely many components. All right, so its dimension is the sum of the dimensions. So it's the sum from k equals 0 to n of n choose k, which from the binomial theorem is just 2 to the n. So it is significantly finite dimensional as compared to, say, the tensor algebra. All right. The wedge product is multilinear and it's graded. If I take an m-fold an m-fold wedge with a k-fold wedge, I get an m plus k-fold wedge. And likewise, it's associative because it is just the image of an associative algebra, namely the tensor. So again, we get all of that for free by using that it is a quotient of the tensor algebra. So, same old question. Why on earth would you do this? It turns out there are many reasons to do this. Most of them are reasonably obscure at this level. But there is one very important reason to see the exterior algebra at this point. Okay, so we're dealing with a vector space. Vector spaces, the nice transform on vector spaces are linear functions or linear maps. Okay, so recall, a linear map, if I apply it to a sum of vectors, I can apply it to each. If I have a linear map of a scalar multiple, I can pull out the scalar. Okay, linear maps in vector spaces are the morphisms. They are the equivalent of homomorphisms on vector spaces. So, I have a vector space V. I have a linear map running from V to V. Well, I can extend V to make an exterior algebra. So the question that then pops up is, can we make an extension of L? All right. Can I make, we'll call it L bar, that's going to run from the exterior algebra to the exterior algebra. And I want a few things to make sense. One is that this extension should be an extension. So it should do the same thing to V that L does when I think of V as that first exterior power. Now, L is linear. This is a wild vector space. I don't want to keep linearity so much. I want multilinearity. Okay, so again, I want it to be linear in each variable. And can I make it into an algebra homomorphism? Because that's the nice kind of map on an algebra. Okay, so this is an idea called multilinear extension. Now, because the exterior algebra is a sum of powers, all I need to do is figure out what it's going to do on every power. So I'll start with k equals 0 and I'll sort of work my way up and see what I can do. Okay, so when k is 0, it's the base field. It's not going to do anything to the base field. So L bar of any scalar is just going to be the scalar. Okay, when we look at it on the first power, well, the first power is just V, and if you remember from our conditions, we don't want L bar to do anything on V that L doesn't do, so it's not going to do anything else. So L bar of V is just going to be L of V, however L was defined. Okay, so for k equals 2, well, I need to figure out what it's going to do on the basis vector. Okay, so I need to know what L bar of Vi wedge Vj for whenever I is less than j. On the other hand, we want an algebra homomorphism. This is a product. So L bar of Vi wedge Vj should be L bar of Vi wedged with L bar of Vj. But those live in the vector space, live in the first power, and there it's supposed to just be L, so it's just going to be L of Vi wedged with L of Vj. Okay, and that basically does it for me. Whenever I have some long wedge, if I want to know what L bar of that's going to be, well, it's supposed to be an algebra homomorphism, so I break it across each one, but then each one lies in the vector space, and on the vector space, it's not supposed to do anything different, so it's just going to be L of the first wedged with L of the second, wedged, etc. through L of the nth. Now, this actually is unique at this point, so if I can find any other algebra homomorphism on the exterior algebra that agrees with L of V on the vector space, then that homomorphism must be L bar. There's just simply no choice. Okay, so this gives us a very sort of simple way to extend our given linear map to a multilinear algebra homomorphism on the exterior product. And this is a game we can play in lots of places. We could have done it on the tensor algebra. I didn't do it in that screencast. I might put it into the homework exercises, or the exam exercises, sorry. Okay, but we can do it. But then again, why? Why would you do this? All right, so let's see that. Okay, so we're going to take L, some linear map, and we're going to take its extension. Now, I'm going to concentrate particularly on what L bar has to do on the n-fold exterior power. Okay, and you'll see why. Trust me. First off, why do we care about the n-fold exterior power? The n-fold exterior power, okay, so it is spanned by all n-fold wedges with increasing index and distinct elements. Well, there is only one of those. If I have to have n objects from the basis that have to be distinct, well, I have to use the entire basis, and I'm going to put them in some canonical order, starting with my first, followed by my second, up through my nth. So, it's one-dimensional. Okay, well, L bar is multilinear, but if I'm working on a one-dimensional space, there's only one variable, so therefore it's linear on that n-fold power. Okay, but if I've got a linear function on a one-dimensional vector space, the only thing it can be is multiplication by some constant. So then the question becomes, what is that constant? Okay, so let's look a little closer. So I've got my basis v1 through vn, and I'm going to assume that L has matrix A given by alpha sub ij with respect to that basis. So in particular, if I look at L applied to the jth vector, I get alpha ij vi, I running from 1 to m. Essentially, it would be running down the column of the matrix, down the jth column of the matrix. That's what L of vj does. Okay, so that tells me what L of a basis vector is. Okay, so if I want to know what L bar does to v1 through vn, well, it's an algebra homomorphism, so that's L of v1 wedged with L of v2 wedged with L of vn. And I know what it does with respect to each one of those. And there's a typo, yet again, hold on. Okay, so I know what L does to each basis vector, so I can just sort of throw that in and express L of vj in terms of the matrix that I have for that. Now, I've got a multilinear thing. I've got sums in each one of the components. I'm going to need to expand that. Okay, so to expand that, I need to expand each sum at a time while I hold the rest of them constant. All right, that shouldn't be too hard. But just to keep things straight, we're going to throw in some more indices. That should help keep things clear. I know it won't, but trust me. Okay, so I'm going to now sum over, oh geez, another typo, hold on. Okay, so everything in the first component, I'm going to give an index of I sub 1, everything in the nth component, an index of I sub n. All right, and I start expanding. Okay, well, that means I'm going to get an n-fold sum of n-fold sums. All right, and I'm going to have alpha I1 times VI1, alpha INN times VIN, but these are now all scalars, and so they can all be pulled out. And so I get this massive sum. I've got n sums of n terms where I've got this product times VI1 wedge, VI2 wedge, all the way through VIN. Now, so far we haven't used the fact that it's anti-commutative because these are all the same vectors, okay? They are all running over the same basis. There's going to be repetitions in there. All right, so that's going to drastically reduce the sum. Okay, so whenever there's a repetition, I'm going to get a wedge of 0. So that means I need those indices to all be distinct. They have to be V1 through Vn in some order. Okay, but that drastically reduces it. All right, so I just now need to take the summation over all I sub 1 through I sub n, where they're all distinct values. All right, I will have some product of the coefficients, and then I will have, this is V1 through Vn in some order. Okay, but that's the key. I1 through In have to be the ordering of 1 through n, and vice versa. Any ordering of 1 through n is going to appear. So rather than saying, okay, I'm looking at I1 through In all distinct and figuring out how many ways to sum that up, that's going to be summed over the permutations. Okay, I'm looking at permutations of 1 through n. All right, because I1 through In are some permutation of 1 through n, I can view this as some sigma 1 through sigma n. All right, these are going to follow suit, and the sum is now over all permutations of 1 through n. So we're basically summing over the symmetric group. Now, my basis is V1, V2, wedge, Vn. These are not in that order. In particular, I've got all of these terms with all these wedges, but they are all V1 through Vn wedged in different orders. But if they're wedged in different orders at the cost of negatives, I can start moving them around, which is precisely what I do. Okay. Now, I start transposing things. I want to transpose these two at a time until I get it back into the ordering of V1 through Vn. And if you remember from Math 370, every permutation can be expressed as a product of transpositions. Not necessarily unique, but as transpositions. So by transposing any two elements at a time, I can do that. How many transpositions I need, as I said, it's not necessarily going to be unique, so I don't know, but I do know that the sign of the permutation is determined up to parity. So if I do it with 5 transpositions, then any other way I can do it with transpositions must be odd, and likewise for evens. So I'm going to get some -1 raised to some power, and no matter how I do it, it will always either be always even or always odd. So that means I'm taking the sum over the sigma in the symmetric. I have the sign of the permutation. I have these elements from the matrix and V1 wedged through Vn. This is my constant that is defining the map. And what do I have? I have an entry from my matrix where there's 1 per column and 1 per row. And there's never a repetition. All right, I get 1 from every row and 1 from every column, weighted by a negative by the sign of the permutation. That should hopefully look very, very familiar to you. That is the determinant. Okay, so L bar of V1 wedged through Vn, this is the determinant of L times V1 through Vn. Okay, a linear map on a one-dimensional space is multiplication by a constant. This is that constant. Okay, now, that seems very convoluted. Again, why? Because everything we know about determinants really follows from this. Okay? To begin with, if I take a matrix or I take a linear map and I work out its determinant, it doesn't matter what basis I use. That's immediate from what we've just seen. You can show this with a lot of mess and fiddle using change of basis matrices, and then it turns out to be a conjugate, and all of that is a nice computational fact. But remember when I said, well, if you take a linear map, its algebraic extension is unique? Okay, it doesn't matter what basis I use. That algebra extension is unique. So no matter what I do, I'm always going to get the same number. I can't possibly get another one. It doesn't matter what the basis is. All right, so likewise, you prove that the determinant of the product is the product of the determinants. Okay, so it's a group homomorphism on invertible matrices. All right, and again, if you do that by hand, it's kind of nasty. Okay, you have to show that it works for an elementary matrix, and then you can show that everything gets decomposed as elementary matrices and get all. Or you're on a one-dimensional space. The determinant of this is going to be a constant. These two will do the job for you because composition of functions corresponds to multiplying of matrices. These are one-by-one matrices. So it's determinant L times determinant M. Likewise, if your linear map is diagonalizable, well, then I can find some basis that represents it as as the eigenvalues down the diagonal. Okay, well, then if I push that to the determinant, that's going to be the product of the diagonals. The product of the eigenvalues has to be the determinant. Okay, and again, it's independent of basis. It doesn't matter which one I use. So if I use that one, it's fine. Now that's assuming that your matrix is diagonalizable. What happens if it's not diagonalizable? Turns out close enough. There's something called the Jordan normal form of a matrix, which will do that trick for you. And really, this is how we define the determinant in the modern age. Okay? This is the correct way to do it. The determinant, the fact that it gives invertibility. Why does it give invertibility? Well, because that last extension wouldn't be invertible if that constant multiple were 0. And that's the only way it can't be. All right? So that's why the determinant determines whether something is invertible. So rather than these sort of convoluted formulas that we have and these convoluted cofactor expansions and so forth and Cramer's rule, this is really how we define the determinant now. It is literally the unique extension of a linear map to its n-fold exterior power. And it tells us a lot. Okay, so that's why we like the exterior algebra, and in particular why we like its n-fold exterior power. Now, next time, I'm going to start talking about non-associative algebras. We're going to look at a couple of broad classes, but then I'm going to look at very, very specific ones. The tensor algebra, the exterior algebra, are very general algebras, not very specific. The non-associative examples that we're going to look at will broadly define some classes, but look at very specific ones, because non-associative is a pretty wild thing to work with.